Hi everyone, and welcome to Backer Breaks It Down. Today we get to explore the short-run behavior of polynomials. Okay, so what does that mean? It means that we are going to focus on like the x-intercepts and zeros of a polynomial function and really look at what happens at the x-axis. Okay, and so in the polynomial investigation, I gave you these 5 graphs here. And I asked you, what do you notice about the degree and the number of x-intercepts and turning points? Okay, and so you, these are some of your responses. So it says, depending on the degree is how many x-intercepts there will be. Okay, so when the degree is 1, there's 1. When the degree is 2, there's 2, and so on. Another one of you said the larger the degree, the more curves are in the graph. And I'd have to agree, like that is definitely happening the larger the degree gets. There is always going to be an even number of x-intercepts in the graphs with even degrees. Odds will always have an odd number of x-intercepts. So check that out, like our odd degrees are linear, cubic, and quartic. And our quadratics and quartics, like both of their graphs are showing 4. So that was like, I think, an interesting observation. The line crosses the x-axis depending on what the power is. Like the cubic function passes like through the x-axis like 3 times. The number of turning points is 1 less than the degree number. So like a turning point would be like where the function has a maximum or minimum. So like linear functions don't have any of those turning points. Okay, so 0 turning points. A quadratic function turns once. The cubic function, we can see it turning twice. The quartic, we can see it turning and changing directions 3 times. And the quintic, we see it turning and changing directions 4 times. So like 1 less than whatever the degree is, okay? And so these are really great observations of polynomial behaviors. So the number of x-intercepts, which are like the real zeros of a polynomial function, says the graph of a polynomial function of degree n will have at most n x-intercepts, okay? Because if you think about it, like quadratics, like you've studied quadratics like extensively. And yeah, a lot of the times a quadratic has, 2 x-intercepts, but we have seen a quadratic with only 1 x-intercept. We've also seen quadratics with no x-intercepts. So it makes sense that like when we say degree n will have at most n x-intercepts, like our knowledge of quadratic functions kind of like is good proof of that. When it comes to turning points, it says the graph of every polynomial function of degree n has at most n minus 1 turning points. We saw this, okay? And so like if I were given, I'm looking over here at these 2 graphs, and if like I asked what is the minimum degree of these? Well, like in graph number 1, I note that it has opposite end behavior. So that means it's like odd degree, right? It has like 2 turning points. It has 3 zeros. And so like I would have to say that this would have to be like at least a minimum degree of 5. We'll talk about like why is it 5 and not 3, and I'll tell you it's because of what's happening at that particular x-intercept. Okay. So I had you guys, when we were exploring these polynomial functions, I had you do a little GeoGebra activity with this graph right here, okay? And so you'll notice like this is the function of the graph that's currently on the screen. So this is the polynomial p of x equals x plus 2 quantity squared. I'm sorry, the factor of x plus 2 times the factor of x minus 1 times the factor of x minus 3. Okay, now I asked you for what powers of a does the graph cross the x-axis, and for what powers of a is it tangent to or simply touch the x-axis. And so a, like I'm pointing to that exponent here, and that exponent corresponds to the factor that tells us -2 is an x-intercept. So let's like actually go here. It'll work, okay, and explore this like a little bit more together, okay. All right, so here's our function. And right now, all of our powers are 1. Okay, so I want you to focus on A and what's happening, all right? So now A is 2. So this is A is 1. Look at the blue dot. This is A is 2. So when it was 1, it was crossing the x-axis. And when it's 2, it's touching and bouncing off the x-axis. What do you think happens when it's 3? Check that out. It's crossing again. All right. So 1 crosses, 2 touches, 3 crosses, 4 touches, 5 crosses, 6 touches. And notice, like, if you're catching on to it now, like when that exponent is odd, it crosses, right? And it's even, it touches. Odd cross, even touch. Look at the red dot, okay? It's odd, even, odd, even. Green dot, it's currently odd, even, odd, even. Right? And so this is referred to as multiplicity, okay? So multiplicity of 0 refers to the number of times a 0 of a polynomial function occurs. And what's happening at the x-axis, like on the x-axis at that 0 changes. So here we have like a 0. Oh, I thought there was a highlighter. Let me fix that. A 0 of multiplicity 1, like in all 3 spots. And notice it's crossing, okay? They're saying right here is a 0 of multiplicity 3. It's also crossing. It's a little bit flatter the way it crosses, but it's still crossing. Here, we have a multiplicity of 2, and it's touching. So, like, we've been looking at the factored form of a polynomial function, okay? And when we're given the factored form, we can easily tell what the x-intercepts are, okay? Because the factor is written like x minus something, and whatever that something is, it's an x-intercept. The exponent refers to multiplicity, okay? So in its factored form, the exponents will tell us the number of times that the factor occurs. And if it has an even multiplicity, our graph will touch the x-axis and like bounce up. And if it has an odd multiplicity, it'll cross. Okay. So what we're seeing over here in this graph with this factor, x plus 1 quantity squared, right? That factor tells me that I have an x-intercept at -1. And since the multiplicity is 2, and that's even, it's going to touch. And if you look at the graph at -1, that's exactly what's happening. The other factor of x minus 2 quantity cubed tells me that my x-intercept is 2. And the exponent of 3 is odd, so it's crossing the x-axis at 3. You should be able to identify the zeros of a polynomial function from its factored form. And then using the multiplicity, tell me what's exactly happening there. Is it crossing or touching? So you could pause and try problems 1 and 2 and then check back in with me. So in problem number 1, we have the function f of x equals 0.5 times the quantity x plus 1 times the quantity 2x minus 3 squared. So looking at that first factor of x plus 1, this is what I know about it. X plus 1 means there's a 0 or an x-intercept at -1. The multiplicity of that factor is 1. It only appears once. There's like no visible exponent. And since it's odd, that means it crosses the x-axis, because odd crosses and even touches. The second factor, the quantity 2x minus 3 squared, right? When it comes to my 0, it's not as obvious. I want to basically solve an equation, 2x minus 3 equals 0, to figure out what my 0 is. So 2x equals 3, therefore x is like 3/2 or 1.5. The multiplicity of that factor is 2, because that's the exponent. And since 2 is even, it touches the x-axis and bounces off. Looking at problem number 2, our first x factor is 2x plus 1 quantity squared. So if I do the math, this is the zero product property, by the way. Okay, I get that the x-intercept is -1/2. And the multiplicity of that factor is 2. 2 is even, so it touches. And then that last one, x minus 5, quantity cubed, has a 0/5, a multiplicity of 3, so therefore it crosses the x-axis. Right? And so that's how we can further describe behavior, specifically short-run behavior of a polynomial function. Okay, so the factor itself tells us what the x-intercept is. The exponent tells us what's happening, because if it's an odd exponent, it's crossing the x-axis at that point, and if it's an even, it's touching, bouncing off the x-axis at that point, and that's how Becker breaks it down.